So recording. So let me start with a description of the general framework of my talk. So it's not really necessary to understand what will follow, but it's a sort of motivation and a general question which is behind. So general framework. So we start with a semisimple algebraic group G, a split semisimple. So G is split semisimple algebraic group over some field. I guess I don't need a notation for that field. So some arbitrary field. And we first look at the variety of Borel subgroups of G. Or if we don't mind fixing a rational point of this variety, so we just pick up a Borel subgroup and then consider the quotient G by B. Okay. And now we twist this variety by some G torsor. So twist it, the quotient G over B by a G torsor over fields. So let's say over the same field over which G is defined, or over some field extension. So G torsor over a field. Let me call it E, the G torsor. So what we get is the variety X, which can be also viewed as the quotient of E by the action of B. So this is the variety I'm interested in, and more precisely, I would like to understand its Chow ring. So Chow ring. So the ring of closed subvarieties of X modulo rational equivalence. Okay, and so it's known in the case where E is trivial. So if E trivial, then X is just G over B. So it's a cellular variety. And so Chow of X is known. So it's additively, it's just a free group of finite rank. And also there is a way to describe a multiplication. So the ring is known. So now if we, instead of looking at trivial E, we look at arbitrary E, then the object is too complicated. So E arbitrary, Chow of X too complicated. And so the idea is to look well at some other particular case, which is as far from the trivial one as possible, and this will be the generic, the case given by generic torso. So instead of arbitrary E, we look at the case of generic. And what it precisely means to be generic for a G torsor can be defined in different ways, which really produce different things. But well, the most simple way to describe is we embed G into the general linear group, GLN, for some n. And then we look at the quotient map from GLN to GLN over G. And for this morphism of varieties, we take the so E to be the generic fiber of this map. So GLN goes to the quotient GLN over G. So this E will be G torsor defined over the function field of this variety. So not over the original field, but nevertheless, it is defined over some field. And so we want to understand Chow of X now in this situation where E is like that. So of course there is some freedom here. So first of all, if we use this definition of generic, then still we need to make a choice of an embedding of G into GLN. So we need to choose N and then the embedding. But as I also said, there are other ways to define the notion of a generic G-torsor, which will give you something different. But the object we're interested in is actually always the same. So it's doesn't change at all. So if we change the generic torsor, then this ring is still the same canonically. And so it's some concrete object, and in the more concrete situation, some concrete G we are going to work with later, I will explain differently what is the variety one can think of here in this question. Yeah, I should probably also mention that this quotient map has the property that actually the fiber over every point of the base is a G-torsor over a field, and every G-torsor over a field is obtained this way. So the G-torsor, the generic G-torsor is generic in this sense that every other G-torsor is a sort of specialization of the generic one. And in particular, we have homomorphism, the specialization homomorphism from Chow of X, where X is given by a generic G-torsor, to the Chow of another X given by an arbitrary G-torsor. And so if we understand the Chow ring like that in the generic situation, then we also get some information about this Chow ring in general situation using this specialization homomorphism. Okay, so now I can formulate the conjecture, which is not really a conjecture because there are counterexamples to it, but I still prefer to call it conjecture and just say that it fails in some cases and it holds in some other cases. So given G as in the beginning, we consider the Chow ring of X given by a generic torsor, so the variety of Borel subgroups of G twisted by a generic torsor, and map it in the standard way into GK of X, where okay, so here is my conjecture. So the standard map from Chow X to the associated graded ring of the topological filtration on the Grothendieck ring of X, I will write down right away what it is an isomorphism. So conjecture says it is an isomorphism where, so K of X is K0 of X is the Grothendieck ring of X. with the topological filtration. And then Gk of x is the associated graded. Graded ring. So Gi, I guess grading is by codimension, is K of x i's term modulo K of x term number I plus 1 for any I. And so the homomorphism here is the standard homomorphism from Chow x to Gk of x, which is always, so let me call it phi. Phi is surjective homomorphism of graded rings. And moreover, the kernel of phi consists of torsion elements. So it's inside of torsion Chow of x. So it's in general quite close to be an isomorphism. But well, usually there is some non-trivial kernel. And the conjecture says that if we consider X given by a generic G torsor, then this should be an isomorphism. And well, it holds in quite a lot of situations. For instance, for simple groups of the type A and C, and also for some other simple groups. But I'm not going to list all cases where it holds. I'm rather going to go into direction of counterexamples. But before I do, let me also say that the meaning of this conjecture here is that it gives a sort of description for the Chow ring, because the right-hand side is known. So K of x is known. Well, it's actually quite difficult to make some explicit computations with it, but still there is a description. Well, first of all, K of x, the Grothendieck ring itself, is known. And then the topological filtration, which is usually a problem, it's not really a problem here because it coincides with the gamma filtration. Topological filtration coincides with the so-called gamma filtration, which is completely determined by K of x, by the ring K of x itself. And the fact that those two filtrations do coincide comes from the fact that the ring Chow of x is generated by Chern classes. So because Chow of x is generated by Chern classes in this situation. So here, so it can be shown that it is generated, and this implies that the topological filtration is something we actually know. And so this conjecture gives a way to understand the Chow ring of x. And well, let me also give you some equivalent formulation, but actually one equivalent. formulation. So instead of saying that phi is an isomorphism, one can say that the connective K-theory of X which is usually denoted CK of X, is free of torsion. Is torsion free. So in some sense, this is also a computation of the connective K-theory for the generically twisted variety of Borel subgroups. And well, this is equivalent formulation, but one implication. So conjecture implies, well, at least in characteristic 0. And this was shown by Yagita, that the algebraic cobordism of X is torsion free. So algebraic cobordism omega of X is free of torsion. But here we only have one implication, so it's not an equivalent statement, and so it's a weaker property, which probably still holds in general. So as I said, there are counterexamples to the conjecture I'm talking about. So this is why I'm writing conjecture like that. But so Yagita suggested replacement for this conjecture by the statement that the algebraic cobordism of our variety X is free of torsion. And so this, we have no counterexamples to this weaker statement, but it's still quite strong. For instance, it implies that Chow 0 of X is free of torsion. And this is something that is still unknown. So I would say that we are very far from being able to verify Yagita's conjecture in general. So it's still unknown that Chow 0 of X is free of torsion for the variety X given by generic torsor. So if torsor is not generic, then there are examples where it is not free of torsion. But for generic torsor, we don't have such examples. Okay. So last comment, last general comment about the conjecture is that in conjecture, the Borel subgroup B, Borel, can be replaced by any special parabolic subgroup P in G, where special means that there are no non-trivial P torsors over fields. So if we work with some concrete split semisimple group G, then it is known which parabolic subgroups are special. And so we can, oops. And so we can replace B by P. And so when we do, then we start looking at twisted forms of G mod P instead of twisted forms of G mod B, and the advantage is that this is usually a variety of smaller dimension, so has smaller dimension than G over B. And so the Chow ring, well, in the split situation, will have a smaller rank and so on. So we come to some simpler varieties, and so this is usually an advantage to replace B by P. So the statement is then still the same. So for this new variety, G mod P twisted by generic torsor, our homomorphism phi should be an isomorphism. And this statement is equivalent to the similar statement with B in place of P. Okay. So now I'm going to specialize to the spinor group. So from now on, G will be spin with some number. So the split spinor group. Actually, I'm going to work with odd numbers because the conjecture for the spinor group like that is equivalent to the conjecture where G is the spinor group with the next even number, so 2n plus 2. Okay. So this is equivalence for the corresponding conjecture. And this explains why I will only look at odd spinor group, spin 2n plus 1. Okay, so if we take any, not necessarily generic, G torsor E, then it yields a quadratic form of the same field, quadratic form Q, of dimension 2n plus 1, like here, 2n plus 1, and of with split even Clifford algebra, split C naught of Q. Okay, and the variety X we can consider in this case will be the highest orthogonal Grassmannian of Q. X will be the highest orthogonal Grassmannian of Q, which is the variety of n-dimensional totally isotropic subspaces for this Q. I mean, this Q is quadratic form defined on some vector space of dimension 2n plus 1. Okay, and then we consider the Grassmannian, the usual Grassmannian of n-dimensional, of n planes in this vector space, and take the closed subvariety of the usual Grassmannian given by the condition that the n planes we are looking at are total isotropic, meaning that quadratic form is 0 on those n planes. So this defines a closed subvariety of the usual Grassmannian, and this is the highest orthogonal Grassmannian of Q. And in the split situation, if the form is hyperbolic, this variety is of the form G over P for some a maximal parabolic subgroup, which is special maximal parabolic subgroup of our spinor group. And as I said, this is for the variety we can consider. So if now Q is not necessarily split, it's given by some G torsor E, then X, the highest orthogonal Grassmannian of Q, is exactly the twist by this G torsor E. Okay, so what can we say about Chow of X in general? Well, it contains a subring, let me call it C. The subring generated by the Chern classes of the tautological vector bundle. So generated by C1 and so on Cn, which are the Chern classes of the tautological vector bundle on X. This tautological vector bundle is the same thing that we have for usual Grassmannian, just a vector bundle such that over every point given by some n-plane, the fiber is this very n-plane. Okay, and so now we work with orthogonal Grassmannian, but we still have the similar tautological vector bundle, which is a restriction of the vector bundle on the usual Grassmannian. And it has rank n. And so C1 up to Cn are the Chern classes of this rank n vector bundle. Okay. So this is a subring which we understand very well. So first of all, it depends on n only. C only depends on n. So relations between the Chern classes which generate C, well, it's enough to write just one formula. They are given by the equality C check equals 1, where C is the total Chern class. So the sum of all Chern classes starting with 1 plus C1 plus Cn. And C check is the same thing given by the dual to the tautological vector bundle. So it's the same sum, but alternating. And then the equality here, if you just look at graded components, so starting from, well, all positive graded components will have to be 0. And these are exactly all relations which we have for the generators of this subring. So this subring is always the same. It doesn't depend on a quadratic form, only on its dimension. And now, if we come to the generic situation, so now we require Q to be generic, which means that it comes from a generic torsor. But you can also just take a really generic quadratic form of dimension 2n+1, meaning that coefficients of this form are given by variables. And then we need to kill the even Clifford algebra, and we do it in a generic way. For instance, going to the function field of the Severi-Brauer variety of it. Okay, so we can think about generic quadratic form like that. So a generic quadratic form of odd dimension with split even Clifford algebra. And so if Q is generic, then Chow of X as a C algebra is generated by just one element. Which I would like to call E, and which is simply 1/2 of the first Chern class of the tautological vector bundle. Well, it sits in Chow 1 of X, which is torsion-free, and therefore it is uniquely determined by the condition that taken twice, this E will give the first Chern class of the tautological vector bundle. So it looks like we're very close to understand to complete understanding of the Chow ring of X, but actually there are problems. So let me show one problem which appears quite immediately. So let me look at 4 times E squared. So it's 2E squared. Meaning that this is C1 squared. And I said we know relations for the Chern classes of the tautological vector bundle. So this one is 2C2. So we have equality between those two, but we can't divide by 2. So 2E squared in general is not C2. Well, it is not as far n is at least 3. So if n is not too small, then there is no equality like that. And this means that the difference is an element of order 2. So it's non-trivial torsion element. Okay, well, it's easy to show that when we multiply by 2, then we get 0 out of this difference. But why the difference itself is non-zero? Well, we see it going. So the fact that this is non-zero, C going to GK of X. So as I said, we understand completely GK of X. And so we can see that when we map this element there, then we already there get an element of order 2. So the original element wasn't 0. So we don't get a counterexample to the conjecture, to our conjecture, but we already get a non-trivial torsion element here. Okay, so now what can we say about the conjecture? Conjecture for G like that. Well, let me put spin n. Well, it actually holds for n up to 12. Okay, so for n up to 6, it is trivial. Because there are no non-trivial G-torsors in that case. And so the variety we are looking at is actually split. And so there is no torsion at all in the Chow ring. Then for n equals 7, 8, 9, 10, this is related to threefold Pfister forms. So the motive of X is a sum, direct sum of shifts of the Ross motive given or corresponding to a three-Pfister quadratic form. And so using this, one can see that everything is fine in this situation as well. And the last case, 11 and 12, as I already said, those values come in pairs. So conjecture for 11, for spin 11 is equivalent to conjecture for spin 12. Well, the point is here is that Q of dimension 11 splits over a quadratic extension, completely splits over a quadratic extension of the base field, and so on. With some efforts, one can show that conjecture holds in this situation too. And so next cases, next values of n are unsettled. So n equals 13, 14, 15, and 16. So those cases are unknown. So, for instance, for spin 13, there is a mystery with the product C2, C3 inside of the Chow ring. And the big question is if this product is divisible by 2. So the point is that its image, when we go to the Grothendieck ring, is divisible by 2. And so if we can show that it is not divisible by 2, so if not, then conjecture fails for spin 13 and spin 14 as well. Yeah, but somehow it's not clear how to show that it is not divisible by 2, because, well, the only way we can do such things are by going to the Grothendieck ring, and there it is divisible by 2. So, there are some other elements to consider here. If we will show that all of them are divisible by 2, then we will know that conjecture holds for spin 13. But it is open, and so now we come to the value n equals 17 and 18. And here conjecture fails, and this is what I'd like to call the first Yagita's counterexample. Okay. So let me write down what we know about spin 17. So in Chow of X, we look at the following element. It's the product C2, C3, C6, C7, and then E. You remember this was the half of the first Chern class, raised to the power 15. Okay. And the statement is that this element, let's call it X, so this product, X is not divisible by 2, but its image in GK of X is okay, so it looks strange. How can we prove this? How can we prove that X is not divisible by 2 if its image in GK of X is? Well, the point is, well, the idea of proof is that we use standard operations. Use standard operations modulo 2 on Chow ring modulo 2. Actually, this element X sits in dimension 3. So what we do, we apply the third standard operation S3 to X. So it will move us to Chow 0 of X modulo 2. And then we look at the image. So image in GKX modulo 2. And it turns out that it is non-trivial, is non-zero. So to say, the image is not divisible by 2. So the image in GK of X modulo 2 is non-zero. And so the integral representative of this element is not divisible by 2 in Chow 0 of X, and therefore the original element is not divisible by 2. So we sort of extend the initial idea. Instead of directly going to the Grothendieck ring, we first apply some standard operation, and then we go to the Grothendieck ring. So unfortunately, with spin 13, this idea doesn't work. So when it doesn't matter which standard operation we apply to this product, C2, C3 here, the result always becomes divisible by 2 when we go to the Grothendieck ring. Okay, so this idea doesn't work here, but it works there for spin 17. And this gives the first Yagita's counterexample. Okay, so after Yagita published this counterexample, I found a different proof for the same counterexample. So one of the reasons was that I wasn't able to understand Yagita's proof. But anyways, there was also a second Yagita's counterexample, which was about spin 19. So second. And at that time, I failed to do the same for the second Yagita's counterexample. But now, in a joint work with Sanghoon Baek, so joint with Sanghoon Baek, we managed to give a different proof for a second Yagita's counterexample and also go further. So go to spin 21. So this is new. And so this is, so to say, beyond Yagita's counterexamples. Okay, so let me give you the formulas. So what happens for spin 19 in our proof? So we consider again some special element in the Chow ring of X, which is this time C2, C3, C6, and then multiplied by e raised to the power 31. And again, we show that this element is not divisible by 2 using Steinert operations, but its image in the associated gradient of the Grothendieck ring is divisible by 2. And for spin 21, it goes similarly with the element to consider being the product C2, C3, C6, C10, and then again e raised to the power 31. So it's sort of mystery how to find the elements to work with, so I can't explain. So somehow they're found, but I don't really see an idea behind finding those elements. And this is probably why I don't see how to continue. So the expectation, of course, is that we have similar counterexample to our conjecture for G equals spin n with any n, well, 21, 22 is served by this example. So for n starting from 23 as well. And so the first thing to start is to find an appropriate element to work with. And then I would expect that similar ideas will provide the proof. So we provide the counterexample. However, for the values, so spin n for n equals 13, 14, 15, 16, I have no idea what to expect. So no idea what to expect and how to prove. I mean, so one probably would expect that for this pair, the conjecture still holds, but then we need some new methods to prove it. And so here, the conjecture will probably fail. So let me put holds with question mark, fails with question mark. But again, it seems that some new ideas are needed to handle this case. Okay, so this is the situation. And I would like to finish with some comments on computations in the Grothendieck ring we are doing here. Because there are some new ingredients in our joint work. So for spin 19 and spin 21, compared to what was done before. So let me briefly explain what we know about K of x in our situation. So first of all, K of x is the same when we go to the algebraic closure of the base field. So this is because G is simply connected. So we have this equality of rings, so isomorphism of rings, or equality. But filtrations are different. So we have the topological filtration here we're interested in, and it's not the same as the topological filtration there. Okay, but still, when we speak about rings, then we need a description of this object. So since we can go over the algebraic closure, it's a question about split variety. So should be not a difficult one, but still it's quite, this ring has quite complicated description. Well, it's generated, well, let me write K of X bar is generated as ring by the so-called special Schubert classes, classes of special Schubert varieties. So they are numbered by indexes from 1 to n, so E1 up to En. And so additive generators are given by products of distinct EIs. So a product like this EI, where big I is some subset of the set of indexes. Well, in other standard system of generators is given by all Schubert classes, not only the special ones, which are also indexed by the same thing. So subsets inside of the set of indexes from 1 to n. These are free additive generators. So the Grothendieck group is free group on that generators. And then there are Pieri formulas. Pieri formulas for a Grothendieck ring. Of the highest orthogonal Grassmannian, which are quite complicated. So just to formulate them, you need some combinatorial notions, and to apply them, you need to do some combinatorial computations. So it's not very easy, the description of the ring. So now I should probably finish soon. So let me just say that the topological filtration for X bar is just the filtration generated by EIs, in the sense that it's the smallest ring filtration satisfying this condition. So with this inclusion. Okay, and the filtration, we are really interested in the filtration for X itself. Well, here we have elements 2EI minus EI plus 1. So, and this inclusion for any I, and besides of that, we have K of X1, which contains E1. And again, these conditions generate our filtration. So the filtration we are interested in, the topological filtration on K of X, is the smallest ring filtration satisfying these inclusions. Okay, and so this gives us a complete description of the object related to the Grothendieck ring. But since the multiplication formulas are quite complicated, well, the actual computations inside of the Grothendieck ring are not so easy to perform. And so somehow with spin 17, we don't really need Pieri formulas for spin 17. Pieri formulas are not needed. But for spin 19 and spin 21, we were not able to avoid using them. They are needed. But we managed to find some replacement for them. So I personally was quite scared by the combinatorial nature of the Pieri formulas. And so using some tricks with generic quadratic forms and partially generically split generic quadratic forms, we were able to replace Pieri formulas by some, well, we were able to reprove some particular cases of Pieri formulas we needed. Yeah, but well, in some sense, the Pieri formulas do show up in this business, and it looks like when we go further to higher spin groups, we will need more and more information coming from Pieri formulas. So this is one complication which grows when dimension of our quadratic form grows. Okay, so let me stop here. Thank you for your attention and sorry for technical issues.
Yeah, thank you very much. Thank you. Are there any questions? Any question? Is there any question?
So may I ask, is there any correlation with Merkuriev conjecture about rationality of BGs, so that BG is rational retract?
Right. So no, I can't formulate a precise relationship. So I can't say that one conjecture implies the other, but somehow the problem we get here looks very similar to the problem we have with this conjecture about rationality of the classifying space. So. And this also gives a reason to expect that for 13 and 14, everything is fine with our conjecture because everything is fine with the other ones. But as I said, I don't know how to prove my conjecture for 13 and 14. So we do have sort of nice description of G-torsors for spin 13 and spin 14, but it doesn't seem to help in our business with this conjecture. Yeah, and so here one expects that the conjecture about rationality of the classifying space fails. But even if we assume that it does, it doesn't allow us immediately to show that our conjecture failed. So I can't precisely formulate the relationship, but as for now, it seems that they are sort of related. Well, I don't know if it will turn out that our conjecture here will fail for 13 and 14, then we probably won't be convinced anymore that they are so related, but we don't know this yet. Okay, that's what I can say.
Any more questions?
So in your conjecture, if you invert the exceptional primes for the group, will it be true then?
Yeah, it will be true. Yes. Yeah. So in the, for the spinor group, exceptional prime is 2, and so we only can have 2 torsion inside of the Chow ring. And so if we invert 2 in the coefficient ring, then all problems disappear, and yeah, we will get isomorphism. Yes.
And also if say, G torsors admit reduction of structure to H torsors over fields. H is, say, some subgroup of G. And if you know the conjecture for H, can you then deduce it for G?
Well, I didn't think about that, so I can't tell you. So maybe it's a good question to look at.
I mean, this is what happens for the smaller spin groups, up to 14.
Right.
Except maybe H is not always connected.
Okay. Yeah. So
but
I probably should look at this for the case spin 13. Yeah.
But that may be the underlying reason for both the, this conjecture and the rationality conjecture being true for smaller spin groups. I mean, hypothetically, it's all hypothetical.
Yeah.
Okay, so I just wanted to ask, what is known about Grassmannians, like, say, modular cases, like Grassmann 2, 2 to the power n or something like this?
You mean twisted forms of Grassmannians, right?
Yes.
Yeah. So as I said, conjecture holds for simple groups of type A, right? So if so you when you look at generalized cerebral varieties given by generic torsor, then the conjecture holds. So this is completely known and so done. Yeah.
So the spin groups are the only open cases, or?
Wow.
No. Well, you have for simple groups you have half spins, and so yeah, you have in types. In type B, basically the only case which is known is the case of special orthogonal group. Yeah, but there is a lot of open cases, but not so many counterexamples. So the only counterexamples we have are related to the spinor group, and that's true. Yeah, it seems to be quite difficult to construct counterexamples. So somehow Yagita was able to start this business, and so for now it still only goes with spinor groups, with other, but still only with spinor groups.
Okay. More questions? More questions, comments? Okay, if not, then let's thank a speaker. Thank you much.
Thank you.